Let me set the timer. So today I'm going to use a timer to remind me that I need to stop the recording and break it up in 30 minutes intervals. Okay, so can anybody confirm that you can see my presentation? We are on the exercise 2.
I can see it.
I'm so sorry, I didn't hear you.
Yeah, we can see it.
Okay, perfect. So last time we ended here discussing this problem. So let's go and look at it and try to solve it. Again, for initial rates, what you're looking for is going to be a concentration that remains the same and a concentration that is changing. And usually that concentration that is changing usually doubles. It could triple, but then you'll have to go 3 to the n is equal to whatever you found out the rate to be. So in this case, we have 1 and 2 as a common one. So we can start with that one. And we are going to, why did I choose 1 and 2? Because I see these are equal. So let me just put 2 lines there saying that value is equal. So that means that the other value is going to change. And this one, the other value, the other concentration changes by a factor of 2 going from 1 to 2. So in going from 1 to 2, I'm going to put an arrow. We are keeping the concentration of NO equal, but we are changing the concentration of hydrogen gas by a factor of 2. And so when you think about the rate constant, the rate constant is going to be K, the rate is going to be equal to the rate constant times the concentration of NO to the power of something, M, and the concentration of O2, of H2 to the power of N. So if you notice here, we're keeping this is a constant, we're keeping this one constant because we are not changing the concentration of NO. So the only thing we're changing is concentration of hydrogen, and we're introducing a factor of 2 on the concentration, which is elevated to the power of N. So the difference between rate 1 and rate 2 is going to be 2 to the power of N, where 2 comes from this factor here, and N is the exponent for the hydrogen. So I'm looking at hydrogen here, and looking at the exponent, which is N. So 2 to the N, and then I'm going to look in here and see what effect that doubling of the concentration of hydrogen has on the initial rate. So when I look at this is 7. This would be, if I make this 10 to the minus 5, then this will be 14. So I have gone from 7 to 14, it has doubled. So the effect is going to be doubling. So that means that N is equal to 1. And that way I figure out what the N value is. For figuring out which the M value is, I need to look at the concentration of hydrogen remaining constant. So when I look under this column here for the concentration of hydrogen remaining constant, I can see that 1 and 3 work. So this is getting very busy. So let me see if I can erase what I have written so far, because now we're going to do the analysis for we can keep now. Let's see what's actually okay. So let me do this in blue. So what we're going to do now is going to figure out what does it depend on a node. So we need to look at H2 and find the value that is equal. So these two are equal. So we're going to, and then the NO 1 and 3 are the ones that we're going to use. and the value of hydrogen remains the same. The value of nitrogen monoxide increases by a factor of 2 and going from 1 to 3. So we're going to go in this direction, 1 to 3. And so again, these two are equal. These two have gone up again by a factor of 57. Yeah. This is like 5.7 times 2, times 2 is 11.4. So that has increased by a factor of 2. And so, okay, so now we know that the NO is we're introducing again the rate constant. Rate is, excuse me, the rate, you see, I say rate constant, I mean rate. So the rate is equal to the rate constant times concentration of NO to the power of M, concentration of hydrogen, and we know that this was to the power of 1, so I'm going to just leave it like that. Now, if I double the concentration of NO, I'm introducing a factor of 2 to the M. And now I'm going to see what happens when I go from 1 to 3 in terms of the rate. So this is the rate. So it goes from 7, 10 to the minus 5 to 28 times 10 to the minus 5. So that's a factor of 4. 4 times 7 is 28. So what exponent of m gives me 4? And the answer is square. So 2. 2 to the 2 is equal to 4. So 2 squared is equal to 4. So m is equal to 2. So now I know that the rate is equal to the rate constant times concentration of NO to the power of 2, concentration of H2. That's it. So notice that the coefficients here are 2 for NO and 2 for hydrogen. Those do not have any say or any consequences. We cannot take the coefficients and think that, oh yeah, these are going to be the coefficients. As you can see, NO has a 2, which coincides with that, happens to coincide with that, but hydrogen has a 2, but the power is 1. So just be careful when you do the analysis. You need to really look at the data. So by looking at a chemical reaction, a balanced chemical reaction, you cannot find out the kinetics. The kinetics needs to be based on experimental data. So let's no, it's not going to let me go through. So last time we were doing this and switching. So, okay. So in this case, we were here, then here. So here's the generic rate law again for the analysis. Let me see if I can make it bigger. So, and we need to find the values of n and m. And that's what we try to do. And then comparing trials 1 and 2. Why 1 and 2? Because that keeps the NO constant and the concentration of hydrogen multiplied by 2. Times 2. And then we do 1 and 3. Why? Again, because if we take 1 and 3, we are going to keep the concentration of hydrogen equal and the concentration of NO doubles. And therefore we can find n is equal to 1 and m is equal to 2, as we said. Oops. So to calculate the rate constant k, then we can, since we know already that this is the coefficient, excuse me, the exponent of NO is squared and 2, and the exponent of hydrogen is 1, we can substitute into this equation. We know if we take any line here, and let me see which one they have taken. They have taken this one here, the very first one. You could take any of those, any of the 3. So the rate is equal to K, concentration of NO squared, concentration of hydrogen, as is depicted here. So if we want to solve for K, K is going to be equal to the rate divided by concentration of NO square concentration of hydrogen. So I'm just doing algebra here. We're solving for the rate constant. And so the rate constant on the bottom line here, the rate constant is going to be, here's the value of the rate, R, and here's the concentration of NO squared, and the corresponding concentration of hydrogen. And so that way we can calculate the rate constant. And again, all of this data has three significant figures, so our rate constant will come up with three significant figures. So that's how you can find the rate constant. So this is a very powerful method to be able to figure out the kinetics. And that is not doing just one reaction, but doing the reaction several times with different concentrations and figuring out what the initial rate is. Questions? Okay, so interrupt me if you have questions. So now we're going to start with today's subjects, and we're going to see the rate, how the rate is affected by concentration. So we know that R, the rate of a reaction, is K concentration of A to the power of M. At least if there is a second reactant, then it's going to be concentration of V to the power of M. So these are concentrations, and these are factors that are going to affect the rate constant. So it's obvious that the rate. So the rate is going to be dependent on the concentrations. Okay, so here we have this equation, which is the reaction of NO, and this is something that happens in polluted air. So we have nitrogen monoxide gas and ozone, part of urban pollution, to produce oxygen gas and NO2 gas. And we have the expression for the rate. So we're telling us that it's first order on NO. What does it mean, first order of NO? Notice that here the concentration of NO is, there's no exponent, which means that is 1. And so the order of a reaction is going to be the exponent. So it's something like this. The order of the reaction with respect to NO is first order. The reaction with respect to ozone is first order. If this will be V squared, then the reaction with respect to B is going to be second order. So we give an ordinal number, first, second, third order, depends on the exponent. Okay, so again, to be able to react, as we said, these two molecules, this is A and B have to come together and collide. And so here we have A and B coming together. We have here two of them coming together and colliding with the oxygen, with the ozone. So you have 2 and 2, then you have more probabilities of collision, and the more you have, the more probabilities of them colliding. So as a result, increases the number of collisions. And that's something we discussed earlier, and that's central. As I mentioned before, that concept is central to understanding kinetics. So in the laboratory this week, we're going to do a reaction and determination of the order of the reaction. That means we're going to try to find the exponent. We're going to do two approaches, but what we're going to be doing is acquiring data for the reaction and trying to see which is the order. Now, the reaction, let's say, the rate of the reaction is equal to the rate constant times the concentration of, let's just concentrate in one component. This slide is about just one component. So to the power of n. So we can run the reaction and we put it, and then we follow with respect to time. Notice that all these plots here have time on the x-axis. And on the y-axis, we have the concentration. So if we look at this very first one here, this is the concentration of A or X. And so we follow how the concentration changes with respect to time. And we can do that using the spectrophotometer in the laboratory by looking at a color solution or a color component of the solution and finding its absorbance. Remember, Beer's law tells us that the absorbance is proportional to the concentration. So, and the proportionality constant is the molar extinction coefficient that we calculated in the previous laboratory. So by looking at the absorbance, we can actually figure out what the concentration is, and then we can plot concentration versus time. So when you run a reaction, the reaction is not like it has a mind. It depends on the reaction mechanism on how it's going to behave and how fast it's going to go. So when we run a reaction, we don't know the order, but usually it's going to fall into, actually here there are 3 categories. The first one is called zero order. And so this one here, zero order. And this is the least likely to happen, but it happens from time to time to come across one reaction that is zero order. Most of the time it's going to be first order or second order. And so we need to figure out which of these expressions. So because this is the this is the excuse me, this is the rate law, and if it's first excuse me, if it's first order, that means that the n is equal to 1. If it's second order, that means that this is 8 squared, and if it's zero order, it will be concentration of A to the power of 0. And when you exponentiate anything to the power of 0, it gives you 1, which means that then the rate of the reaction is going to be equal to the rate constant. And so you can see, you will see the reaction going at the same rate all the time until it's exhausted. And that's unusual. Usually they can slow down, as we mentioned yesterday, but it is possible. And so when we have the data of concentration on the y-axis, and on the x-axis we have time, and we have the data, the numerical data, then we can plot this equation here. Of this plot, we can make this plot here. When we take the concentration, we put it on the y-axis and versus time. If it gives you a line, that means that the reaction is behaving like a zero order reaction. And what you will observe when you look at your data points, that your data points are going to be more or less on a line. They're not going, when you do kinetics, they're not going to be perfect, but they're going to be very close and they're very obvious. So you can do a linear regression and find out what the slope of that line is. In general, this when you plot concentration versus time, it doesn't look like this. And most of the time, it will look like this. So your data points are going to look like this. So obviously is not linear. There's a curve to them. And so therefore, if you get this kind of plot, the second kind, and you do concentration versus time, if you get this kind of plot, that's telling you that it's not zero order. So then you take the logarithm of that, so you create another column where you take the natural log of x, and you calculate here the values, and there will be a calculated column. In the lab quest, what you do is you add up a calculated column, and you take the natural log of x. So when you go into calculated column, it's actually for a formula, and they'll give you a menu of formulas. One of them is going to be natural log of x. And so you create that, and then you plot this natural log of x versus time and see if it's linear. A lot of times it's going to be linear. So then you know that it's going to be first order. But it might occur that when you plot natural log of x versus time, it's going to give you still a curve. And that would mean that then the reaction is not following this equation with an exponent of n is equal to 1. And therefore, you actually go again and calculate another column, which is going to be 1 over x, the inverse of the concentration of x, and then you plot it. Usually, one of these three plots is going to give you a straight line. And so this is concentration. This corresponds to concentration of x to the power of 0. This concentration of x to the power of 1. This corresponds to concentration of x to the power of 2. If none of them are linear, that means that you have a different exponent, and there'll be a different plot that you need to do. In the laboratory this week, what we're going to do is we're going to collect the data, which is going to give us directly, or no, it's going to give an absorbance. So we need to calculate the concentration of x, then we calculate the natural log of x, and then 1 over x. In the laboratory, what is going to happen is going to be that you're going to get, sometimes you get two lines, you get something that is more or less linear here. And so instead of looking like this, it looks a little more linear. And so you need to figure out, these two look more or less linear there because they're not perfect and they're experimental data. Then you have to decide which one is the best. And for that, you look at the linear regression and look at what is called the correlation coefficient. And the correlation coefficient is usually called R. Could be lowercase or uppercase r. And R is going to be between 0 and 1. So that's the range. So usually in math, we do this from 0 to 1. The closer it gets to 1, the better. So then you can compare the correlation coefficients or these two equations that look more or less linear and figure out which one is the best. And then you go with the best value of R. The best value of R is going to be the one closest to 1. Sometimes the correlation coefficient becomes negative, and that is fine. You will take the negative. Doesn't mean anything in terms of how close it is to the line. So you just take the absolute value of the correlation coefficient, and then you select that to be the linear line, the linear plot, and therefore that will tell you which is the reaction order for the reaction. Okay. The equations that we see here, we're going to go now in more detail, and we're going to look at the equations that go with each one. So in a problem, in the course, they can tell you, oh, this is first order, or this is second order. They could give you the order and ask you, what is the concentration of this compound after 30 seconds, for example, or after 50 seconds, or after 10 seconds. So for those of you, you're going to use these equations here. And these are called the integrated rate laws, because to be able to figure them out from the equation, from this equation here on top, you will have to do some integration. We are not going to do integrals. We are just going to have them. So I recommend that you write this, or you can plot this. You can print this. This is in your book. If you find another one, you can also print it. But have them handy, especially when we're taking the test next week. But now we're going to go into this. So we're going to start, I think, with the first order, second order. So we're going to know which they are more likely. So more likely first order, then second order, then zero order. Okay, so now we're going to go to the first order kinetics. First order means that the coefficient is n is equal to 1. And we're going to look at the reaction here. This is ozone. Again, this is something that happens in polluted air as well as in the ozone layer. That means the ozone is sensitive to light, and light can break it down into oxygen, gas, O2, and atomic oxygen. And the rate law, as you can see here, is first order. So there's the rate constant here, and here is the exponent equal to 1. So n is equal to 1. That 1 is not written like this. With these ones here, the coefficient of 1 here are not written. So the coefficient here is not written, but it's a 1. And then you do the integration. Don't worry about the integration. We're not going to go unexpected to do the integration. So here's an example of the reaction. And here you can tell this plot here is slightly curved. It's not a straight line. So notice that they have plot concentration. How do I know? Well, concentration is here. The word concentration is here. But if I wouldn't know, I can look at the units, and the units are molarity, the units concentration, and this is time in seconds. And here's the data, the table of concentration versus time. So notice that they have taken the natural log of the concentration of ozone, because now they're going to test it against the first law. So they're going to, I guess, probably, they told us already that it's first, so they're verifying that it's first. So let's go to the next slide. Did we manage? Yep. And now here you have the natural log of ozone versus time, and you can see now clearly that it is a straight line. And it looks pretty good for an experimental. Okay, so the equation here is the equation of the line. So they have plotted, this is y is equal mx plus b. Y is the natural log of ozone. X is the natural log, excuse me, X is the time. And so the slope here is going to be minus k. So when you write a rate, you say rate is equal k concentration of ozone, right? And to the power of n, where n we know that is 1. Oops. So that is the rate of the reaction. And I forgot now. Disappearing, bother my computer. Okay, so the rates of the reactions usually will say like the speed. The speed that doesn't. You say let's say you're going from home to school. So you're going at 70 miles per hour in the highway. So and when you go from school back home, you're still going at 70 miles per hour. Technically, you're going in the reverse way. So if we think of the speed at which you're going, the speed has a direction, and therefore you have one is the negative of the other. In this case, the rates, when we look about rates of reaction, they're always we consider them positive. And so we could write negative, and that means, okay, it's disappearing, but we can talk about the rate of a reactant as positive as well. So do not get bothered by it. It's like a check. When you write a check, if I write a check for you or a transaction that is going to be put into $10 into your account from me, that means that the check is, or the transaction is for $10, is going to be negative to me, is going to be positive to you, but still the transaction involves $10. So the $10 is kind of an absolute value. Is that you can say, oh, this is minus $10 or this is plus $10, because it depends on which angle you're doing. For you, might be plus $10. For me, it's going to be minus $10 to my account. So that means that when we talk about rates of reaction, a lot of times you're going to see positive values. And so don't get confused by that. We are taking the absolute value. Okay. So we're going to different reactions. So we have finished this. So my timer went off, and I'm going to stop the recording for a second and restart it again. This is much easier for me to